When writing music, we often begin with just a melody. For example, let's take the melody O Tannenbaum. This sounds alright, but on its own, it's pretty empty. We need to add some chords to turn it into a song. For our project, we utilize online planning to generate chords for any given melody.
Most existing approaches leverage large deep learning models, such as transformers, to generate music, with prominent startups such as Suno AI taking this approach. A few notable examples of AI-generated songs are BBL Drizzy and We Are Charlie Kirk. In this project, we leveraged a simpler approach, utilizing only Monte Carlo Tree Search, tuned to our own musical preferences, a far more computationally efficient approach than deep learning.
Naturally, we can formulate harmony generation as a Markov decision process. Let's return to our earlier example of O Tannenbaum. Say that we've already predicted the first 3 chords, and we want to predict the 4th one. First, the state space is the current melody note as well as the previous few chords as context. Second, the actions are simply picking a chord from the current measure, with the action space being the set of all possible chords. We can then assign a reward corresponding to how well the selected chord fits the measure. A transition occurs when we then move on to the next measure, which is deterministic.
To implement an algorithm that accomplishes this, we had 3 main components.
Pre-processing the data is fairly simple conceptually. We just section the melody into how we want the parts to be harmonized.
We then had to design a reward function that numerically quantifies the quality of each chord. These criteria can be split up into 3 broad groups. The first are the correctness rewards. Since we want the harmony notes to fit with the melody notes within that measure, we can test their overlap. The more overlap, the more reward, and will penalize when there are any notes present in the melody not in the chord. For music theoretic reasons, we weigh the importance of the characteristic notes of the chord more, and we also weigh long melodic notes more than the shorter ones. The second are the sequence rewards. In jazz music, there are common patterns that harmonies take on, one of which is the 2-5-1. We reward the model when the predicted chord completes one of these sequences. The last reward is for uniqueness. In short, it's just a penalty for duplicated predictions. This was added as an incentive for the model to come up with more interesting results. The total reward is simply a linear combination of these 3 sub-rewards, and the parameters were chosen manually.
We then ran Monte Carlo Tree Search to select the sequence of chords that will maximize the rewards. From our experiments, a policy-based approach didn't generalize well, and running Monte Carlo Tree Search is still computationally reasonable given our search space. We chose to use MCTS with the UCB1 exploration heuristic, as it allowed us to search through promising chord progression efficiently, and we always selected the highest scoring candidate chords.
We ran O Tannenbaum through our algorithm for 3 spiciness levels, which, along with creating a 3 Blue 1 Brown style video, was our additional 30-hour contribution. But first, as a baseline, we generated an example with random chords. We can see that it doesn't fit the melody well, which it gets penalized for. For the mild level, only simple chords were used, and we can see that the algorithm hits many of the correct notes, as well as some sequence bonuses. For the hot spiciness level, more complex chords were added to the action space, and this allowed the chord progression to contain all the notes in the melody while retaining the sequence bonuses.
For the extreme spiciness level, we removed the restrictions on what chords were available, which resulted in this hella hip result. To visually see the improvement, we plotted the rewards accrued by the various approaches.
To recap, we implemented a Monte Carlo Tree Search algorithm to create a jazz harmonizer. Through careful parameter tuning and musically informed reward functions, it can generate stylistically appropriate harmonizations.
However, our approach had several limitations. First, the look-ahead procedure required an entire melody to be composed beforehand, preventing real-time use. Also, the system does not currently incorporate any dataset-driven learning.
For future work, we hope to apply Bayesian optimization for advanced hyperparameter tuning, leverage our corpus of music score files to build a more informed model, and ultimately extend our system to operate in real time for interactive live performance.
Speaking of live performances, let us conclude with a live reharmonized rendition of John Coltrane's Giant Steps, generated entirely by our algorithm, performed with a few of our friends.
2, 3. And ultimately extend our system to operate in real life. In real life? It's already in real life. No!